Hi everyone, welcome to this third and last part of Introduction to Wireless Power Transfer. In the first two videos we have seen an introduction, we talk about the different WPT technologies, then we focused on inductive WPT and its operation and modeling, and today we are going to deal with power converters used to the implementation of IPT systems, inductive power transfer systems. So we will see several possibilities, non-resonant converters, resonant converters, and finally we will talk about feedback and regulation. So let's start with non-resonant IPT converters. Here we have an example using a half bridge, then a blocking capacitor, DC blocking capacitor to supply our IPT system, and then we have an output stage to implement our rectifier or multiplier to get the required output voltage. This solution has very few components, so it provides low cost. The implementation is easy and design also is quite easy to perform. They are robust against short circuit and no load operation without any special configuration or protection circuit. But the main problem is that they exhibit higher RMS currents compared with resonant solutions, and therefore the efficiency of the circuit is going to be lower. So here we are showing one possibility, but we could use any other converter, like maybe a full bridge converter and so on. And also we have several possibilities for this output stage. One possibility is just to use a full rectifier in order to get DC voltage at the output, but in some cases we can be interested in getting higher values of the output voltage, so we can use a voltage doubler as shown here, or even a voltage quadrupler as shown here in this circuit, so we can get an output voltage much higher in this case. Here we can see the equivalent circuits of a non-resonant IPT converter. What we are doing with our converter is to apply a voltage square waveform at the input, as we can see here, V1. And because of the operation of the output stage, we are going to have also a square waveform here at the output of the IPT systems. So we are going to have this voltage V2, which is also a square waveform with an amplitude equal to the output voltage, but with a phase lag with respect to the input voltage V1. This type of circuit is quite easy to analyze. It is better to go to this other equivalent circuit using the pi equivalent circuit of the IPT system. For this we can use the equations that we have seen in previous presentations, and then with this the converter is quite easy to analyze in order to obtain what is going to be the value of the output voltage and the value of the different currents, the phase lags, and so on. Here we can see some of the results of this analysis. We can see the waveforms, the input voltage of the IPT, the output voltage here, the one of the currents that is circulating through the inductance LA here, and then we have other waveforms, and finally we have the current at the output and so on. So with these equations here we can obtain the value of the output voltage. This is the voltage ratio, and then we can obtain also the phase lag of the current, which is also very important to analyze the behavior of the circuit. We have here the parameters and so on. I'm not going to enter more into detail about the operation of this type of converters, because you have here in this video Power Electronics number 2 entitled Non-resonant converter for inductive power transfer. You have all the information related to this type of converter. So if you are interested, please take a look at this video. So let's talk now about resonant IPT converters. Here we are showing the block diagram of this type of converters. We have our inverter here. It can be a full bridge as shown in this figure, or it could be also a half bridge. The bridge is going to generate a square waveform here at the output, and then this waveform is applied to our IPT system. In order to make the operation resonant, like a resonant converter, we are going to add an input stage or even an output stage also that are going to incorporate passive elements as capacitors or even inductors. So the idea of these input and output stages, which are also known as compensation circuits, is the following. We can reduce the harmonic content and obtain sinusoidal operation at the input, so the current that we are going to have here at the input is going to be sinusoidal, so the EMI also generated is going to be lower. They are also used to achieve zero voltage operation. In this way, we need an input current that is going to be lagging the voltage generated by the bridge, so we can provide zero voltage switching for the switches. Also, it's important to have an input power factor here at the input high in order to decrease the RMS current that we are going to handle here at the input, and therefore reduce the conduction losses in both the switches or even in other elements that we have in our system. So summing up, the idea of using these compensation circuits is to increase the efficiency of the whole system. There are two basic compensation circuits. One is the series compensation and the other is the parallel compensation. Let's start by the series compensation, which is shown here in this slide. The idea is that we are going to have always an inductor in our system because it is the inductance corresponding to the coil that we are using in our IPT system. So if we add a series capacitor as shown here, then we can operate our converter at resonant frequency. So the equivalent impedance of the series inductance and series capacitance is going to be negligible. So we have this equivalent circuit in which the output voltage is going to be equal to the input voltage. For this, we have to operate our circuit under this condition, which is that the frequency of our converter is going to be equal to the resonant frequency, which is obtained with this expression here. So the output voltage is going to be equal to the input voltage, and therefore the current that is going to circulate in our circuit can be obtained with this expression. In order to operate our circuit with low distortion and quite sinusoidal operating waveforms, we need a value of the quality factor which must be high enough. The quality factor is given by this expression here. So in order to get a high value of the quality factor, we need a small resistance in the circuit. So this type of compensation is useful for low voltage applications because in this way we are not going to have an excessive value of the current circulating in the circuit. The other compensation circuit is the parallel compensation. So here we have an example in which we have our voltage source, an inductor, a capacitor, and then our load R. So we can make an equivalent circuit here, which would be as shown in this circuit here. This part of the initial circuit can be made equal to a current source with a value V1 over omega L, and then we have our inductance L, the capacitor C, and the load resistance. If we operate this circuit at resonant frequency, then the parallel combination of L and C is almost equivalent to an open circuit, to an infinite impedance. So our final circuit will be like this. So we have a behavior of a current source applied to the load. So at resonant frequency, the output current is going to be like shown here, is the voltage V1 divided by omega 0, which is the resonant angular frequency times the inductance L. So here the behavior is opposite to the behavior of the series compensation. Here the behavior is similar to a current source at the output. In this case of parallel compensation, the quality factor has this expression here. So in order to get a high value of Q, we need a high value of the load resistance R. So the conclusion is that this type of compensation is useful for high voltage applications in order to avoid an excessive current circulating through the circuit. Let's see an example of resonant compensation circuit. This is one of the most common compensation used in this type of systems, which is the series resonant compensation circuit. Here the idea is that we have our IPT system. This is the model that we have seen in previous presentations. So in order to do the compensation, we add a series capacitor here at the input C1 and another series capacitor here at the output C2. So adding these two capacitors, C1 and C2, what we are going to do is to make them resonate with the inductances L11 and L22. So the operating frequency is going to be selected to fulfill this requirement shown here. In this way, the input current is going to follow this expression. This is the output voltage and this is the output current. So some of the features of this type of compensation are shown here. We have a current source behavior at the output. As we can see here, the current follows this expression and is controlled by the input voltage. It's a behavior of current source. Then we have that, as we know, this is a series compensation circuit. So in order to have a high quality factor, the load resistance must be low. So this is suitable for low voltage applications. Another advantage is that the input current is always in phase with the input voltage, as we can see here, independently of the load and the coupling. So we can assure that we are going to have a high input power factor at the input, and we can also provide zero voltage switching, even though for this it is better to have an input current which slightly lags the input voltage. One disadvantage is that the output voltage depends on load and coupling, as we can see here in this expression. The output current does not depend on the load, but it depends on the coupling. And finally, a disadvantage is that if we operate with no load, we are going to have a very high current at the input. So it's necessary to implement some kind of protection against no load operation. Here we can see other possibilities of compensation circuits. We have the series parallel compensation circuit in which we are adding the primary capacitor in series here C1, and then on the secondary we have the capacitor in parallel. So here we have the parallel resonance at the output, so this is more suitable for high output voltage applications. And then we have the other two possibilities, the parallel series compensation with a parallel capacitor at the input and a series capacitor at the output. So this is interesting when we have a behavior of current source at the input and voltage source at the output. And then finally we have the parallel compensation circuit in which we place a parallel capacitor at the input and a parallel capacitor at the output. So we have a behavior of current source at the input that supplies the system, and then we also have a behavior of current source at the output, and of course many others that we can find in the literature. Now talking about output power regulation, we have two basic methods to implement the regulation of the power. We have constant frequency control and variable frequency control. In the constant frequency control, we usually employ some kind of method to control the output power. For example, here, using a full bridge inverter with phase shift control, is possible to generate here an output waveform that can be controlled in amplitude, and therefore we can control the power that we are sending into the output. So here we have some features regarding this type of control. The design of compensating circuits is easier. When we operate at constant frequency, we are going to have a lower EMI because we are keeping the switching frequency constant. However, it's more difficult to maintain optimum operation against changes in the distances in the IPT systems or changes in the load. We are going to have higher switching and conduction losses when we have a variable coupling, and in general we are going to require more components. The other possibility is to use variable frequency control. So in this case we can keep, for example, the inverter simpler because we can use only a half bridge inverter to generate here a square waveform, and because in the rest of the elements we have a behavior in which the impedances change with the frequency, then we can do the control of the output power. This is easier to maintain optimum operation because we have the frequency as control variable, so it can provide lower losses and better efficiency, less component count and reduced size. But the problem is that we are going to generate more EMI because of the variable frequency operation. Regarding feedback and regulation, there is an important challenge here in IPT systems and in WPT systems in general, because we want to avoid any mechanical connection between the emitter and the receiver, but we need to send information from the output to the input to operate in closed loop and do the regulation of the output current or voltage. So here are the main goals that we have to fulfill. We need to avoid any kind of physical connection between the output and the input, but we need to do the regulation of the output voltage or output current against perturbations and against changes in the coupling of the system. And also, in some cases, we need to do the control of the output power by the user. One possible solution is to use digital communications via radio frequency signals. So we are using here a transceiver at the input to control the power converter, and then another transceiver at the output to do the measurement and send the information to the input. For the communications, there are many possibilities, many different protocols. We can use a dedicated radio frequency solution. We can use Wi-Fi, Zigbee, Bluetooth, and so on. It can also be unidirectional or bidirectional. Of course, bidirectional can provide more flexibility. It can be also integrated in the primary digital control, so we can implement the communication in the primary using a microcontroller, DSP, and so on. A very important parameter in this solution is the bit transmission rate of the communications protocol, because this is going to affect the dynamic response of the system. So this must be chosen with care. And the main disadvantage of this solution is the high cost, because we need a transceiver at the input, another transceiver at the output. Usually we employ high-end integrated circuits like microcontrollers to implement these transceivers. So usually this is only employed in high-end, high-power applications, like for example in electric vehicle charging. A simpler solution is to use the IPT system itself to transmit the information. So this can be done in two ways. We can use a signal injection in parallel, as shown here. We are injecting a signal into the IPT system, and this signal can send information into the primary side. So here we have the receiver, and here we have the transmitter. We are using a high frequency signal operating at a frequency much higher than the waveforms that are used to send the power from the input to the output. So then we can superpose this signal to them and then send the information into the primary. And another possibility is to do the signal injection in series. So we can do like this. We can use a coupling transformer to inject the high frequency signal, and then using another coupling transformer we can get the information on the primary side and finally send this information into the power converter. Here we can see two solutions to simplify this sending of the information from the secondary to the primary of the system. One is the resonant tank modulation. So what we are doing here is that we are connecting and disconnecting a parallel capacitance. So with this we can change the behavior of the resonant tank, and therefore the amplitude of the signal is going to change a little bit, not so much to interfere with the power sent into the load, just enough to send information from the secondary to the primary. And the other possibility is the load modulation. So here what we are doing is connecting and disconnecting a parallel resistance in parallel with the load. So in this way we are also affecting the output a little bit. So this is going to be received also from the primary side, and with this we can send the information into the power converter to do the regulation. Well, with this we come to the end of this presentation and this series about wireless power transfer. I hope that you find these presentations interesting. Please let me know if you have any comment or question. Thank you very much for watching, and I hope to see you in the next video. Goodbye now.